In most of our mathematical education, we learn specific ways to demonstrate graphs and functions. Today I want to highlight the usage of polynomial functions and the idea of finding the roots of these equations using a method developed by Isaac Newton in 1685. We define a polynomial equation as a combination of classical algebraic tools, such as x squared, cubed, adding terms, subtracting them, and so on. We define the order of the given polynomial by the highest power leveraged within the polynomial equation. What we now want for some polynomial equation is the knowledge of when it is equal to 0. This implies finding the function's values when it equals 0. You can see this with every polynomial function like the shown function right here. The function visually equals 0 when it is having an intersection with the x-axis. This implies that y is equal to 0, and since we always graph the functions in a xy fashion, this means that the function equals 0 at that point too. The mathematicians among you might know how to call these specific points, and they call roots. For the specific functions graphed here, the roots can be roughly approximated by using your bare eye, but the question I want to ask you today is whether you can compute them specifically, and if so, how do we actually do it? And yeah, for all mathematicians among you, this might seem like a very reasonable thing to do, but if you walk up to a complete stranger on the street or in the bank and ask them whether or not this might be a reasonable thing to do, he would think of you as being quite crazy. But as in a lot of other fields of math, there's quite a lot behind the computation of roots of a given polynomial equation. Let's take the field of computer graphics for example. The computation of roots of polynomials is useful in computer graphics for solving various geometric problems. One of the most common applications for polynomial root finding in computer graphics is the intersection tests. In computer graphics, we often need to determine where a ray intersects with an object. This is useful for rendering images as it allows us to determine the color of a pixel in the image by tracing a ray from the camera through the pixel and finding where the ray intersects with the objects in the scene. The problem of finding the intersection of a ray with an object can be formulated as finding the roots of a polynomial equation that describes the object. For example, if we have a sphere with radius r, then the equation of the sphere is given by the polynomial equation x squared plus y squared plus z squared equal to r squared. When we then add a ray to the scene, we now want to know when the ray and the sphere intersect. Without getting into the bare details of this, we can say that we find the coordinates of the intersection point by finding the roots of a quadratic equation, which sets us back on the computation of real roots of any given polynomial equation. Placing a dot at the intersection point, you can visually see now when the ray is intersecting the sphere and when not. This technique can also be extended to other types of objects such as planes, cylinders, cones, and all sorts of geometric objects by defining appropriate polynomial equation. The real ability to find the roots of these equations efficiently is crucial for real-time rendering in computer graphics. This particular example is just here to emphasize the importance of computing roots in the real world. But as many of you might have already asked yourselves, and as I have asked myself before making this video, we have ways to compute roots, don't we? And although this statement is totally true, it is also kind of wrong. Picture a quadratic equation for example. It is given by the equation f of x is equal to ax squared plus bx plus c, and we graph the function as a parabola on the xy plane. The interesting thing here is that we can visually see the roots, and what is more important is that you can compute these roots via the well-known quadratic formula. We can evaluate and compute roots via this formula, making it very easy to compute any kind of root of a quadratic equation. Before stepping on into higher order polynomial functions, it is worth taking note here that the quadratic formula was previously used when I showed you the example of the intersection points of a ray and a sphere. Analogous to this are calculating when a light ray, for example, hits a certain object. This can be very useful to know when you are rendering shadows and lighting in animation movies such as the famous Ratatouille, where they used the quadratic equation tons of times calculating certain light intersection points. So calculating roots is a very interesting and very important thing to do. Moving on to cubic equations, we can also define a formula for that, which looks a little messier. For cubic, we define its roots by the following formula. We can technically also define a quartic formula, so a formula for calculating the roots of degree 4 polynomials, but what is way more interesting is that when you get to degree 5 polynomials, is that there's no possible way to have a possible formula for computing the roots of a quintic or higher polynomials. This is known as the unsolvability of the quintic, and it has been rigorously proved that this cannot be done. So to calculate the roots of such functions, we need to think of something different, and that's where Newton's method comes into play. And here's how it works. Let's say we have a given function f of x and we want to compute one of its roots. We start with a random guess, let's call it x0. In most scenarios, the output of the given polynomial, so f of x0, is not going to be 0, but some other value instead, which can be understood as the height of this graph at that point. To get closer to the real root, we ask when a linear approximation of the function at x0 equals 0. So when does the tangent at f of x0 cross the x-axis? So the general question is, how do we calculate the difference between the old guess and the improved guess that we got by visualizing this tangent line? Since we have a polynomial function, we can always take its derivative, and this gives us knowledge about the slope at f of x, since it is given by the function f prime of x0. And this gives us a nice visual convenience. If we want to find out the slope of that linear approximation, it's like looking at a gradient triangle with a given rise over run property. The height of the graph at x0 divided by the step from the root of the linear approximation to our initial guess gives us the slope of this linear approximation. Really think about that for a second, because it is very, very crucial here. So for the slope, we now can say that the slope is equal to f of x0 divided by the step we take. And since we know what that slope is, because it's just the derivative of the function which is given by the derivative that we decided earlier, it has a nice algebraic meaning that the derivative at x0 is equal to f of x0 divided by the step. If we rearrange this equation, we get a reasonable idea for what that step size is. The step is now just equal to f of x0 divided by f prime of x0. What we can do now is just take our initial guess and subtract the step size from it, which gives us a new guess. And if that's confusing to you, or if you don't really know what this f prime stands for, just take a look at an old video I made about the derivative of e to the x, where I explained more about the derivative. Or take a look at some amazing videos, for example made by 3Blue1Brown, about the essence of calculus. But moving on, we can see that we now have a new and approved guess where we can just do the same procedure. Take the derivative at that point, which is visualized by the tangent line, and then we calculate the given step size and subtract this from the new guesses we made after all. By doing this over and over and over again, you can, in theory and also in practice, determine the root of any given function with perfect accuracy. What I want you to notice here is that it is a seemingly easy procedure, and that there are many ways to conduct this and go far beyond just calculating the roots of polynomials. But before we can discuss any of that, we have to take a look at some issues that also can derive from Newton's method. Let's take a look at the same function as earlier, but let's shift it upwards a bit. The new representation is just a little different since I scaled the axis a bit. Now we can use the same guess as before and let Newton's method do its job. After a while, you can clearly visually see that the new guesses always just go around some local minimum or hop way out of range. But then they finally go to the true root of the function. Here the guesses converge to the root as expected. This shows that Newton's method can have its difficulties, but it finds its general root most of the times. What I mean by that is that there's way more behind the hopping out of range which we saw. And to be clear for the end, this procedure, this algorithm of tracking down the roots of any given polynomial, is extremely useful in many cases where you have to find the root of any polynomial. We saw some foreshadowing of this in the computer graphics example, but it's also very helpful in machine learning, physics, and signal processing. I especially want to learn more about machine learning and neural networks, where we're going to talk about in some future episodes. But last but not least, I want to give the engaged students of you a little homework. Newton's method isn't just useful for finding roots of uncomputable polynomials, but also for calculating square roots by hand. Given any quadratic equation like x squared minus 7, for example, can you find a way using Newton's method to calculate the square root of 7? I am looking forward to your answers, and I will thank you all for watching, and I hope I see you in the next episode.